Bismillah ar-Rahman ar-Rahim. I am honored to introduce my work to the third International Online Conference on Molecular Modeling and Spectroscopy. The present study, entitled Simple Processed Polyvinyl Alkyl Multi-Wall Carbon Nanotube Semi-Transparent Nanocomposites for High-Performance Optoelectronics. In this study, we are concerned with the development of lightweight, flexible PVA multi-wall carbon nanotube nanocomposites with enhanced optical and electrical properties prepared by the simple solution casting technique for several optoelectronic applications. A systematic investigation of structural, optical, and dielectric properties of this system are discussed by different tools and techniques. The variations of the optical and electrical properties of dielectric of PVA with different loading levels of multi-wall carbon nanotube suggests that this nanocomposite can be used in optical shielding materials and electronic devices. All samples were prepared and measured at the nanoscience laboratory for environmental and biomedical applications in the Department of Physics, Faculty of Education, Ain Shams University. Generally, polymer nanocomposites have many applications in several purposes, such as aerospace and marine structures, automotives, sports goods, chemical storage tanks, pressure vessels and pipes, also in biomedical applications such as medical implants and X-ray tables, and electrical applications such as panels, insulators, connectors, and switch gears, and in many other applications. Our materials in this research article are polyvinyl alcohol in granular shape, which was supplied by Alpha Acer Chemicals, and multi-wall carbon nanotube from Graven Chemical Industries Company of Turkey. Nanocomposites of PVA multi-wall carbon nanotube were prepared by the simple solution casting technique with various multi-wall carbon nanotube weight fractions ranging from 0 to 0.925 weight percent. In this simple technique, we have PVA granules and multi-wall carbon nanotube. Both powders were dissolved in deionized water and stirred. The polymer stirred for about 24 hours at 40 degrees, and the multi-wall carbon nanotube was also dissolved or dispersed in deionized water for about 6 hours stirring at 40 degrees Celsius. The mixture of the two solutions are then sonicated for 1 hour and poured to Petri dish. The obtained film were then peeled off the Petri dish, and it was flexible, and this is one of the same images of the PVA multi-wall carbon nanotube nanocomposite. It is observed that the PVA multi-wall carbon nanotube nanocomposite, except a semi-crystalline nature, represented by a diffraction peak at 2 theta equal 19.5 degree, corresponding to the 101 plane crystalline atactic phase of PVA, with d spacing of about 4.653 angstrom. The incorporation of multi-wall carbon nanotube did not reveal any change in the diffraction peak angle compared to pure PVA. And also there is no additional diffraction peaks observed corresponding to the multi-wall carbon nanotube even at high concentrations. After filling PVA with multi-wall carbon nanotube, the peak intensity at 19.5 is slightly decreased. This resorts to the interactions between the polymer and the multi-wall carbon nanotube, which leads to a decrease in the intermolecular interaction between the polymer chain segments and the degree of crystallinity. The optical transmission and absorption spectra of PVA multi-wall carbon nanotube films shows that the unloaded PVA has a high transparency in the visible region. All absorbance spectra have clear peak in the region of UV at lambda equal 235 nanometer for both pristine PVA and PVA multi-wall carbon nanotube nanocomposites, which is related to pi-star transitions of aromatic carbon-carbon bonds. For all investigated samples, no other absorption peaks were observed at higher wavelengths, as mentioned before by several researchers. The shift in the absorbance edge in the multi-wall carbon nanotube doped PVA samples refers to the changes in the band gap and may be caused by the changes in the crystallinity of the host polymer or forming charge transfer complexes. The direct and indirect energy band gap, optical energy band gap, can be obtained from two correlations. For allowed direct transitions, M equal half or R equal half, and for indirect transitions, R equal to. The direct and indirect optical band gap can be obtained by extrapolating the plot of both alpha h nu to the power half and alpha h nu square versus H nu, the photon energy H nu, which represented in this figure. The values of the energy band gap, direct and indirect, are given in this table for different concentrations of multi-wall carbon nanotube. The value of both EG direct and EG indirect are shown to be decreased with the addition of multi-wall carbon nanotube due to the unstructured defects, which increases the localized states density in the band gap. Also, from Arbach relation, Arbach tail energy was calculated from this figure, log alpha versus H nu, and the values of Arbach energy was seen to be decreased, to be increased with increasing multi-wall carbon nanotube content. Inversely with EG, due to the increase in the disorder of BVA by multi-wall carbon nanotube addition. This also means that the addition of multi-wall carbon nanotube tends to redistribute the energy states and allowing many possible transitions through bands to tail and tail to tail. The refractive index N for the investigated samples are calculated using different relations. For using both direct and indirect optical energy band gap. This figure represents the values of refractive index obtained for direct band gap, and this figure represents the values of N obtained using the indirect band gap. From these two figures, it is obvious that the obtained values of the refractive indices calculated by these different approaches have the same behavior and increase with increasing multi-wall carbon nanotube weight percentages. This increase in the refractive index may extend the usefulness of these materials for optoelectronic applications as anti-reflection coatings. This means also that the addition of multi-wall carbon nanotube to BVA matrix introduce a denser nature and lower band gap material of these samples, which in turn increase the value of the refractive index. The optical dielectric constants are also calculated from both direct and indirect energy band gap values of N. High frequency dielectric constant epsilon infinity and the static dielectric constant epsilon naught. The values of epsilon infinity are increased for both direct and indirect, and the values of epsilon naught decrease for both direct and indirect, with increasing the weight percent of multi-wall carbon nanotube in the BVA matrix. These results suggests that the optical and the dielectric parameters of BVA multi-wall carbon nanotube can be controlled by the addition of multi-wall carbon nanotube filler. The nonlinear optical parameters such as Chi1, Chi3, and N2 are also obtained for BVA with different loadings of multi-wall carbon nanotube. The magnitude of nonlinear refractive index N2 is approximately doubled from 1.29 times 10 to the power minus 11 for pure BVA to 3.08 times 10 to the power minus 11 ESU for 0.925 weight percent of multi-wall carbon nanotube. This means that adding multi-wall carbon nanotube to BVA suggests an investigated nanocomposite with interesting properties to be applied in nonlinear optical application and can be controlled by the concentration of the multi-wall carbon nanotube. Optical limiting power sensitivity is also an important parameter studied for the investigated samples. The normalized power versus the concentration of multi-wall carbon nanotube shows that this normalized power decreased rapidly with increasing carbon nanotube or multi-wall carbon nanotube concentration. Here we see that increasing the multi-wall carbon nanotube content tends to decrease the normalized power, and the optical limiting of the nanocomposite films depends on their response to absorb or scatter the incident light beam or incident laser beam. It has been noticed previously that the reduction in laser intensity is fundamentally related to the structure and continuously the transmittance response of film at the same laser beam wavelengths. The studied dielectric properties of the investigated samples include dielectric characterization, epsilon dash, dielectric constant epsilon dash, and dielectric loss epsilon double dash, and also AC conductivity. From these figures, it is clear that the increase in epsilon dash of the sample by increasing the percentage of multi-wall carbon nanotube. This increase is attributed to the increment of material aggregation in the electrical field, and which causes dipoles collisions leading to the produce of heat. It is also obvious that epsilon double dash decreases exponentially with frequency, which can be described by the space charge and electrode polarization. These results suggest that the relatively high dielectric constant and low dielectric loss of the investigated nanocomposites, which may be promising candidate for use in high frequency capacitor implementation. It is also observed that by plotting ln sigma AC versus ln omega, the increase in AC electrical conductivity in terms of frequency, which resulted of the ionic movement facilitated by the pathways formed because of the incorporation of multi-wall carbon nanoparticles or carbon nanotubes content. It rises for the different nanocomposite film in the frequency region owing to the increased mobility of the charge carriers. And from this relation, the frequency exponent is which can be calculated, and the values of the frequency exponent are shown to be nearly or near unity and decrease with increasing the multi-wall carbon nanotube content. This result supports that the conduction in the investigated samples may be by the correlated barrier hopping model, and the mechanisms regulating the transport of charges in the nanocomposite films are very important for basic science and technical perspectives. Thank you very much.